So we can think of a solution forming as occurring in 3 steps. So before you make the solution, you have a solvent and you have a solute, and when you make the solution, you're putting them together and they're going to mix. So in order for them to mix, the solute particles have to separate from each other. That involves breaking or overcoming the intermolecular forces that were holding them together. So that's going to be an endothermic process. You have to put energy in. So we'll call that the change in energy for the solute. We also have to separate the solvent particles to make room for the solute particles to come in. That will also be endothermic. So delta H for the solvent will be greater than 0, a positive number. When we mix the solute and solvent particles together, that will be exothermic because energy is being released. As the particles which are attracted to each other come closer together, energy is released. So we'll call this the energy change for mixing of the solute and the solvent, and that's going to be a negative number. Okay? The enthalpy of solution is the sum of all of those changes. And so the overall sign, whether it's positive or negative, is going to depend on the magnitudes of those, because 2 of them are positive and 1 is negative. So the change in enthalpy for the solution can be positive or negative. Do you remember back in experiment 6B, the styrofoam cups? And the second part, we looked at a step 1 and step 2 for the reaction. And step 1 was just taking the copper sulfate and dissolving it in water, and the temperature went up. There's not really a chemical reaction occurring, but the heat of solution was negative, because when you dissolve copper sulfate in water, it releases energy. So it was exothermic. Other things, when they're dissolved in water, absorb energy and are endothermic. So if we're mixing green and purple, what we're imagining here when we're talking about this is that we're taking the purple solute particles, and we're separating them from each other. And that requires energy, so this goes up. And then we take the solvent particles and we separate those. And that requires energy. Then we allow these particles to come together, and that's going to release energy. In this case, it released more energy than we had to put in. And so this is a net exothermic process. Over here, we're thinking through the same process of separating the solute, separating the solvent. But when these two come together, it doesn't release as much energy. It releases less energy than was put in. And so it's absorbing energy from the surroundings. Why does this solution even form if the energy is higher? It's a new word we learned today, entropy. Entropy. Because when these are mixed, their energy is dispersed, and that is one of the driving forces of nature. So now we're just going to talk about aqueous solutions. So we can combine 2 of those terms, the change in enthalpy for the solvent, so taking the solvent particles apart, that's the water, and the enthalpy change for mixing, or the heat of mixing. Combine those 2 things and call that the heat of hydration. So the delta H solvent, delta H mix, we're going to call that delta H hydration. That's what you were measuring when you measured the Q for dissolving copper sulfate in water. So we had this, the heat of solution is equal to the heat of the solute plus the heat of the solvent plus the heat of mixing. we're going to combine these two terms and call them the heat of hydration. Delta H solute is endothermic, so this one's positive, that one's negative. The sign of the heat of solution is going to depend on which one's larger. This heat of hydration, no, not that one, this one. Delta H for the solute, that's taking the solute particles and separating them, which is the opposite of the lattice energy. The lattice energy was taking the separated particles, and when they come together, they release energy. So delta H for the solute is the same number as the lattice energy, just different in sign. So here we're looking at potassium fluoride dissolving in water. So in order to separate the potassium particles, that is the opposite of the lattice energy. So that is equal to negative of the lattice energy. Lattice energies can be looked up in tables. And then here we have the heat of hydration. That can be measured. That happens to be minus 819 here. So now we have these hydrated, and the difference is the heat of solution. That can be either positive or negative. If this is positive, it means that energy is coming into the system, and it will get colder, feel cold. If it's exothermic, if it's negative, that means energy is being released, and the solution will feel warm. Any questions?